Hello students, just recording this video to walk you through some of the ways that you can determine things like the constant flow rate or restricted hour flow rate for a storage basin or a storage tower that you have some design data for. So the data that I have here is taken from the lecture slides. And I'm just going to show how we go about getting the values for the uniform pumping rate, 14-hour pumping rate, storage, and various other things. And it will hopefully enable you to then go on to the tutorial question and, in a similar fashion, complete that problem, being able to work out those solutions there. So where do we start? Well, the first thing is to convert these this flow rate in meters cubed per minute into an hourly flow rate. So we're dealing with hour-long blocks here, so we want to work out how much flow is actually taking place in that time. So let's see here, we're going to, how will I label this? Firstly, the value will be meters cubed per hour. That cubed symbol, by the way, is hold down Alt and hit 0179 on the number pad. Okay, and this is our flow, and we have the meters cubed per minute rate by 60 is the meters cubed per hour rate. I'll copy that down for all of those hours. Okay, after that we need to add together all of the flow values to build up a cumulative rate. So as the hour progresses through the day, we need to work out how much total flow there has been up to that point. So see, again we're dealing with, this time rather than meters cubed per hour, we're dealing with just meters cubed. So we're going to sort of take that hour value out of it, and we're cumulative flow. This you could also call your demand for the day. Might actually say demand. So for the first hour, it's just the flow rate for that first hour, and in every subsequent hour, it is the flow for the current hour plus whatever the previous rate has been. Right, so now all of these cells should be referencing the cell immediately to their left and the cell above, so it's carrying forward that flow volume. Okay. So if we wanted to work out for this cumulative demand what the total flow rate would be, so the constant flow rate, we could determine that average flow rate in meters cubed per minute. So go back to that rate. That's going to be equal to the total flow that we have. So this row here is the critical one. So we have 24 hours of flow up to this point. That is the kind of total volume. The point below is sort of continuing the loop back to the 25th hour into the next day. Alright, so for this value we have the total flow over the 24-hour period divided by 24 hours and 60 minutes in every hour. So we find that our meters cubed per minute flow rate is nearly 18 meters cubed. Alright, so now if we were to work out the way that the supply of this water would look over the 24-hour period, we can similarly, using the meters cubed unit there, this is going to be another sort of cumulative thing, and this will be instead our supply. So for our supply this time, we are now taking our average flow rate, multiplying that by 60 to find out how many meters cubed we are going to pump into the system each and every hour. And the formula to just kind of work out this continuous flow rate is the initial rate plus the rate in the previous cell. So in this case it's going to be referencing H5 twice, but in subsequent cases when we copy it down you'll see that we're referencing the cell one up and also sticking with H5 in that exact cell reference. So drag that the whole way down and you'll see that at the 24-hour mark we have this value matching. So our demand has been calculated to equal our supply. If we were to plot a graph of this demand and supply, so let's see, we want a scatter plot. That kind of plot will do as well. Oh, isn't Excel clever sometimes? Really knows what we want. Except that we don't want that there. I think it's not exactly figured out what we want. We'll have to just change that a little bit. So this should be our x values, should be our hourly rate, and our y values should be that value there. This is for demand. And if we edit this one, our x value is again the same hourly portion. Our y value is the supply, and the label there, supply. Okay, so let's make this graph a bit bigger. So we can see over the 24-hour period, our constant supply in red climbs up so that it exactly matches the demand. But in the various parts of the day, the demand lags behind the supply, and in other parts in the day, the supply lags behind the demand. At this portion of the day, we're going to have a region in which the supply has filled our storage unit, whatever it happens to be, a quite significant amount. The vertical distance between those 2 points is the amount of overfill currently in the tank. And as we continue to move up to this top point, this is the amount of excess demand. So at this point, our demand will be above the supply, and so that that difference there will then be a sort of an extra storage requirement also of the tank. So we can, by looking at this graph, get an estimate of how much volume of tank we're going to need. More accurately, we can add in another column in here. Try and make some space a bit. So we can determine the difference. And this is again going to be in meters cubed. The difference between supply and demand throughout the day. So we're just going to take a direct difference between these two. So you see at the 24-hour mark again we have no difference. That's where it matches up perfectly. At all of the points we have some values. This point where we have quite large values of difference in here, this is where our supply is over our demand, and then we have in the negatives where our cumulative demand has exceeded our supply, and we would need that extra bit of reservoir in the tank to be filled in that point. If we wanted to work out the total required volume in meters cubed, we could take the maximum value found anywhere in this column, which is going to be a large positive number, one of these 4,000-ish sort of values corresponding to that region, and we can subtract from that the minimum value found in the column. So the most negative value, the point where the demand has exceeded the supply. And we would find that we need almost 6,000 meters cubed as a sort of minimum amount. If you had a tank, your water tank had significantly large increments in size, obviously you can't ring up the tank manufacturer and ask for a tank 5,931 meters cubed in volume. Your next tank up might be 6,500 or something like that. So we might give it some sort of rounded up figure depending on our available increments of size. So far this has just looked at the straight flow for regular demand. We have not yet made any allowance for this column indicating the fire flow requirement. And so we've just calculated the average flow rate and the required volume based around that. So we now ask the question, or what if instead of pumping directly for our 24-hour period, we were instead pumping for a much more narrow 12-hour period between, I think in this problem's case, 6 a.m. and 6 p.m. So this period throughout the day. If we were going to do that, then we would need to sort of vary our values a little bit. So we still have the flow rate that's going to stay the same, and our cumulative demand will stay the same, but our supply and the difference will vary. So I might just hide these cells, and I'll leave the graph over there. We'll vary that in a minute. So now we're going to need to work out our flow rate. So this will be 12-hour flow in meters cubed. Oops, forgot the meter first. Meters cubed per minute. So for 12 hours, we're again going to take this 23-hour value of cumulative flow and divide by 12 hours of pumping and in 60 minutes in an hour. So we now find that we're dealing with a larger 35 meters cubed every minute to maintain our rate. Now if we have our cumulative supply, again in meters cubed, we're going to have this pumping rate by 60 minutes in an hour. So we find that we are now providing some 2,000 meters cubed in every hour, except that we're not starting pumping at the first hour of every day. We're actually starting pumping at 6 a.m. So we'll drag that down to there. I think that's in line with 6. Every subsequent hour adds that much water to the system, until after a few hours we have, just before we switch the pumps off at 6 o'clock, we have our required total daily flow. So you can see there now that these two cells, the flow in 24 hours matches the pumping rate in 24 hours. And all of the other flows, this one's just equal there. So our cumulative rate from 0 to 6 a.m. is just 0, and after 6 p.m. is still our maximum value. Okay, again we can plot a graph of this. So our demand hasn't changed, but we now have a different supply. So our supply now takes the following shape. For the first part of the day, demand gets a significant lead over supply until we turn the pumps on, when supply quickly catches up and exceeds the demand. And then there's this portion of the day where for everything after 6 p.m. all of the water that is going to be needed by the general populace will be kept in the tank. So it needs to have that much water space in reserve. As we had done in the past, we can determine the difference between these supplies, and this difference is also going to be meters cubed. So the difference between our cumulative supply and our cumulative demand will appear as shown. So again, we're only really interested until the end of the 24-hour period, not counting this first hour of the next day. Our required volume in meters cubed, we can work out the same way we worked it out before. So we say that the maximum value occurring in here minus the minimum value occurring in there. This will determine our required volume. So we're now just above 10,000 meters cubed, probably rounding up to 10,500 meters cubed. Again, based on our sort of available tank sizes. Okay, so far we hadn't really looked at the effect of the fire flow and what that will do to our sort of available sources. So in addition to our flow, how am I going to hide these? I might insert a new cell in here, and we'll call this fire flow, or flow plus fire. There we go. Flow plus fire in meters cubed per hour. So that's our current flow rate plus the fire flow rate times our 60 minutes in an hour. You'll see after the fire flow rate is no longer counted, then we are dealing with just our regular flow rate as being equal to our fire flow rate. So all of these values are identical, whereas these have varied. Our cumulative demand should now consider the fire flow. We're going to take that on instead and drag this down like so. So we've bumped that up a bit. I'll hide this cell. So now we're dealing with our fire flow. We've got our flow rate there counting all of these values, and our cumulative demand for the day also counts the requirement for fire now. So we've sort of automatically updated the flow rate that would be required there. We don't necessarily have the same max minus min value that we were sort of working with before, because the addition that we have here, this sort of climbing section of the demand, is sort of assuming that the fire demand will always start at the start of the day, which obviously isn't the case. Our fire demand for 10 hours of 10 meters cubed per minute could start and end at any point in the day. So we're allowing for that, rather than sort of adding a continual value and looking at the difference between supply and demand as we had in the past. When we're determining the required volume, we are really, so I should hide that value so it's less confusing. We're really taking the value that we calculated earlier, and we are directly adding on 10 hours of continual use at 10 meters cubed per minute. So the fire volume on its own will be that 10 hours times 10 meters cubed per minute times 60 minutes in an hour. So some 6,000 meters cubed. And the total volume is the sum of the above terms. So the value that we'd calculated earlier for the daily service, plus at all times a 6,000 meter cubed fire reserve volume that firefighters might draw on at any part of the day. Our flow rate can be counted as just the same, because we are effectively over that whole period of the day making up the extra 6,000 fire flow volume. And you would imagine that if you had extreme weather and you needed to continually pump water to fight fires, then you would also be able to turn the pumps on for the remainder of the day. So rather than having just this period and this period with no pumping, you'd be able to pump continuously. Okay, I don't believe that I have missed anything there. Right, if there are any questions about this, obviously you can come and see myself or Andrew. The tutorial problem has some questions and answers available in the back of it, so you can try this same problem yourself. So we have here a new set of design data, new question rates, and some answers down there that you can work through. Again, if you're not able to get any of these answers, or you're not aware of the logic involved in using them, you just come and see us and we'll point out the thing to do. I suppose probably worth noting that in this problem, rather than starting at 6 AM and finishing at 6 PM, which meant that we kind of had a flat part and then a rise and then an end, in this problem you'll be, for your not 24-hour period portion, you'll be starting at 6 PM and finishing at 8 AM. So that will mean that your supply will sort of start over here, and then we'll jump back up over here and we'll carry on. So that you don't get confused, I'll mention now that you will also need to rework your demand so that demand starts at the same time as supply, and then you should be able to apply the same logic that we've gone through here in determining your solution. So that problem data is available there. And as I said, the answers are in the bottom of the tutorial sheet. I will put this spreadsheet with my example that I've used in this YouTube video, as well as the problem data for your question, up available on Moodle. Okay, I hope that that's all made sense to you, and I'll see you in the tutorials.